Welcome to Newton's first law. We have a ball bearing on a plate, you see it here, and the plate will accelerate. What will happen to the ball bearing? Well, let's take a look. And the plate accelerates, and if you looked well, we'll play it again. You will see that the ball tries to stay at the same place. It's only when he touches the end, he will receive the same acceleration as the plate. Now we'll do the inverse. We will have a moving plate with a ball bearing on it, and suddenly the plate will stop. What will happen to the ball bearing? Let's look. So you see the ball bearing on the plate. I move, I stop, and the ball bearing continues until he hits the edge. Let's look at it again. So it's a bit like you in your car, and the car suddenly stops and you want to go through the front windshield. So this is the same situation. Now we will change direction. Ball bearing on the plate changes its direction of motion. What will happen to the ball bearing? Let's take a look. Now follow the ball bearing with your eyes, and you see the plate is pulled towards me, and you see that the ball bearing wants to keep its straight trajectory. So he goes to the other side. It's a bit like when you're in a car and you take a turn. You will have the feeling that you want to go to the other opposite edge. In fact, it's you that wants to go in a straight trajectory. Take a good feel about it next time you're in a car. Well, here we have a final little movie. We have a ball bearing on a tablecloth, and I will do the same with a ball bearing on a smooth table. I've used my car keys as a means to accelerate the ball bearing and to give him about each time the same horizontal force. And the first force, you'll see, the ball bearing, he stops rather quickly. But on the smooth table, he will keep going, because friction is much lower. So in fact it's friction that stops him. So to put it in words, when an object has no net force acting upon it, the object will remain in rest, or it will keep a constant velocity. Say it in other words, an object is in rest, that is in rest, remains in rest, unless there is a net force acting upon it. Or an object with a constant velocity on a straight trajectory remains with that constant velocity on that straight trajectory for as long as there is no net force acting upon it. I like to put focus on the word net force. It means there can be several forces on the object, but as long as those are equal, there will be no change in velocity. But if there is a net force, then you will have a change in your situation. For example, a space probe on its way through the solar system. It just keeps on going. It needs no extra motor or extra accelerations to keep it going. It just has nothing to stop it, so it keeps on going. A bit like the ball bearing on my table. It just keeps rolling and rolling. Of course, in the end it will stop because there is still friction. But the less friction, the longer you will go. No friction, you keep on going. Or, in a frontal collision, the body of the driver keeps its velocity, and it will go through the front windshield. That's why we have to wear a safety belt. Now, let's look at an example, a more elaborate example of a skydiver, and sometimes difficult to grasp for some people. Here we have an airplane, and I drew a nice skydiver. The skydiver is in free fall, jumping out of the airplane. At that moment, we have a force of gravity working on it, acting upon it. So Fg is m times g. G is the gravitational constant, m is the mass. Gravitational constant, gravitational pull. Here 9.8 Newton per kilograms. And the diver accelerates, and so after a while we have friction. A short while. The friction, which is dependent upon a constant, the constant of the form of the skydiver, its aerodynamic form, times the velocity square. So if you double your speed, you quadruple your frictional force. So after a while, the friction force will be as big as the gravitational force. And those two are equal, so there will be no resulting force. And the skydiver would fall at a constant velocity. So in free fall, after a few seconds, he will reach speed about 180 kilometers per hour, and he will keep falling with that speed. Now what happens when he opens his parachute? Let's take a look. The skydiver opens his parachute. The gravitational force is still the same, but this time the frictional force is much bigger because his C value is also much bigger because of the form his parachute has. It's much bigger than a small skydiver. Now, this force is bigger than this one. He does not go upwards, suddenly, but the net force is upwards, so he slows down. There's an acceleration upwards, so his speed downwards will go down. When his speeds go down, his frictional force will go down too, and even quadruple. So, rather quickly, his frictional force will be the same again as the gravitational force. So the skydiver slows down, the frictional force reduces until the forces are equal again. And we have again constant velocity. So he has a safe speed to touch down. Well, I hope this clears about Newton's first law. Let's go to second law in the next movie.